Gazing upward at the night sky, humanity has always felt a stirring, a quiet pull toward the stars. It is not merely curiosity that drives us, but a profound yearning, a compulsion to step beyond the boundaries of our world. We are not content to remain tethered to this pale blue dot, our cradle. Our hearts beat with the rhythm of the cosmos, urging us to reach for distant worlds, to touch the unknown, to weave our story into the vast tapestry of the universe. This longing is not new. It echoes through our myths, our dreams, our science, and now it finds form in a bold vision, a new method to propel us across the interstellar void, a concept born of ingenuity and ambition, a system we call T.A.R.S, torqued accelerator using radiation from the sun. This is no mere fantasy, no fleeting wish cast upon a shooting star. It is a call to action, a challenge to our species to rise above the mundane and dare to dream of interstellar shores. The stars are not just points of light, they are beacons, summoning us to a destiny far greater than the confines of our planet. For too long, we have lingered in the safety of our solar system, our gaze fixed on the horizon, but our feet rooted to the ground. Yet within us burns a fire, a need to explore, to discover, to know. This fire has driven us to the moon, to the edges of our system, and now it demands we take the next step, a leap not just for individuals, but for all of humanity. Consider the stakes. If we remain here, bound to Earth, our story may fade into silence. The galaxy, vast and indifferent, might never know we existed. Our triumphs, our struggles, our very essence could dissolve into the cosmic dust, unnoticed, unremembered. This is one path, Earth as both our cradle and our tomb. But there is another. We could choose to venture forth, to spread our light across the stars, to plant the seeds of humanity on alien worlds. We could become a species that not only survives, but thrives, igniting the cosmos with our presence, our knowledge, our dreams. This is the promise of interstellar travel, the promise of T.A.R.S. The journey begins with a simple truth. The stars are far, impossibly far. The nearest, Proxima Centauri, lies 4.24 light-years away, a distance so vast it defies comprehension. To cross it with our current technology would take tens of thousands of years, far beyond the span of a single life. Yet, the challenge is not merely distance, but the fundamental limits of physics. Rockets, our trusty steeds, rely on chemical propulsion, expelling a mass to generate thrust. But to reach the stars, we would need fuel reserves so vast they would dwarf our spacecraft, rendering the journey impractical. The tyranny of the rocket equation binds us, demanding exponential fuel for linear gains in speed. To break free, we must think beyond rockets, beyond the tools that carried us to orbit. We must reimagine propulsion itself. Enter the concept of solar sailing, a vision as elegant as it is ancient. Imagine a sail, not of cloth, but of gossamer-thin material, stretched taut in the vacuum of space. Instead of wind, it catches the gentle pressure of sunlight, photons streaming from the sun, imparting their momentum to the sail. This is no mere metaphor, it is real physics. At Earth's distance from the sun, each square meter of a perfect sail feels a force of about 9 micronewtons, a whisper of pressure, yet relentless. Over time, this whisper can build, accelerating a lightweight craft to astonishing speeds. Solar sails have already proven their worth. Spacecraft like Japan's Icaros have danced with the sun's rays, gliding through the inner solar system. But to reach the stars, we need more than a whisper. We need a gale. The dream of interstellar solar sailing is not new. A decade ago, a bold initiative proposed firing massive lasers at a tiny sail, propelling a microchip-sized probe to 20% the speed of light. The vision was breathtaking. A fleet of such probes, each no larger than a postage stamp, racing toward Alpha Centauri, capturing images of alien worlds and beaming them back to Earth. But the dream faltered. The lasers required gigawatts of power, demanding infrastructure on a scale humanity has yet to achieve. The costs were astronomical, the engineering challenges daunting. The sails, delicate and vast, would need to withstand intense beams without tearing or melting. The vision, though inspiring, remains a distant hope, a reminder that ambition alone cannot conquer the stars. Yet, from the ashes of such dreams, new ideas rise. T.A.R.S. is born of this necessity, a concept that marries the elegance of solar sailing with the pragmatism of engineering. Picture a ribbon of material, thin as a spider's web, stretching across tens of meters in space. One side gleams silver, reflecting sunlight with near-perfect efficiency. The other is dark, absorbing the sun's rays. This ribbon is tethered at its ends, forming a system that spins in the vacuum orbiting the sun. The difference in radiation pressure, stronger on the reflective side, sets the ribbon twirling like a cosmic pinwheel. As it spins, it stores energy not in batteries or fuel, but in the raw kinetic power of its rotation. This is T.A.R.S., a mechanical flywheel harnessing the sun's endless bounty. The genius of T.A.R.S. lies in its simplicity. Unlike laser-driven sails, it requires no colossal power plants, no arrays of lasers spanning continents. It drinks directly from the sun, capturing its radiant energy at a distance of 1 astronomical unit, where sunlight is strong and steady. The ribbon, crafted from materials like carbon nanotubes, is both lightweight and strong, capable of withstanding the stresses of rapid rotation. At its ends, tiny probes, microchip-sized spacecraft, wait, poised for release. As the ribbon spins faster, centrifugal forces build until, at a critical moment, the probes are flung outward, hurtling into the void at speed sufficient to escape the sun's grasp. This is not science fiction. It is a calculated leap, grounded in the physics we know. To understand T.A.R.S., we must delve deeper into its mechanics. Imagine the ribbon, 7 meters wide and 63 meters long, a mere 2.8 microns thick, thinner than a human hair. Its silvered side reflects nearly all incoming light, while the dark side absorbs it, creating a differential force that drives rotation. The system orbits the sun in a quasite configuration, a delicate balance between gravitational pull and radiation pressure. Unlike a traditional orbit, where a planet's speed is dictated solely by gravity, a quasite uses the sail's reflective properties to reduce the need for high orbital velocity. This keeps T.A.R.S. stable, spinning in place, charging its kinetic battery over months or years. The math is compelling. Using carbon nanotube sheets already available commercially, T.A.R.S. could spin up over 3 years, reaching a rotational speed where the centrifugal force nears the material's tensile limit. At this point, the probes are released, exiting at 40.4 kilometers per second, fast enough to break free of the solar system. This is no mere jaunt. It is interstellar travel, achievable with today's materials and the sun's free energy. A single T.A.R.S. could launch multiple probes, forming a daisy chain across the stars, each relaying data to the next, creating a network to beam faint signals back to Earth. The vision is modest, yet profound. a low-cost path to the stars, built not on dreams of limitless budgets, but on the ingenuity of constraint. But why stop there? The stars demand ambition, and T.A.R.S. can be pushed further. Consider an eccentric orbit, where T.A.R.S. swings close to the Sun at perihelion, harnessing the intense radiation to accelerate faster. This exploits the Oberth effect, where a small boost at high speed yields outsized gains in velocity. Or imagine using stronger materials like graphene, which could withstand greater stresses, allowing higher spin rates. Gravity assists from Jupiter or Saturn could add another 10 kilometers per second, nudging the probes closer to the speeds we dream of. Even the probes themselves could be sails, gaining extra velocity as they drift outward, pushed by the fading light of the sun. Yet there is a bolder trick, one that stretches the boundaries of physics. What if we could enhance T.A.R.S., not with stronger materials, but with electric fields? Picture the ribbon's ends charged, one positive, one negative, creating an electrostatic force to counter the centrifugal stress. This would allow T.A.R.S. to spin faster, far beyond the limits of material strength. The catch: a spinning dipole radiates electromagnetic energy, bleeding away some of the stored power. Calculations suggest this limits the system to a terminal velocity of 1,000 kilometers per second, 0.3% the speed of light. It is not the relativistic dream of laser sails, but it is a 100-fold improvement, a speed that could reach Proxima Centauri in just over 4,000 years. This is the heart of T.A.R.S. Not a silver bullet, but a spark. It is a concept that takes the grandeur of interstellar dreams and distills them into something tangible, something we could build today. It does not promise to carry humans across the void. Its probes are tiny, its G-forces immense, but it offers a foothold, a way to send our eyes and ears to the stars. It is a reminder that progress comes not from waiting for miracles, but from wrestling with the possible. The stars are distant, but they are not unreachable. T.A.R.S. is a bridge, however narrow, to that future. Beyond propulsion, T.A.R.S. holds other possibilities. Its spinning ribbon, charged with electricity, generates a magnetic field, a shield against the cosmic rays that threaten future outposts on Mars or beyond. Imagine a fleet of T.A.R.S. units in orbit around a Martian base, their fields weaving a protective cocoon, guarding fragile human lives against the harsh radiation of space. This is not a mere side effect. It is a glimpse of how a single idea can ripple outward, solving problems we have yet to fully face. T.A.R.S. is not just a path to the stars. It is a tool for survival, a testament to the versatility of human ingenuity. The journey to the stars is not a sprint, but a marathon, a relay race across generations. T.A.R.S. is a step, not the final leap. It reminds us that interstellar travel is a collective endeavor, one that demands patience, persistence, and imagination. The probes it launches may take centuries to reach their destinations, but their journey will carry the weight of our aspirations. They will be our emissaries, bearing witness to worlds we cannot yet touch. And as they sail through the dark, they will remind us of who we are, a species that dares to dream, to build, to reach. This is not the end, but a beginning. T.A.R.S. is a call to the curious, the dreamers, the builders. It asks us to look up, to feel that ancient longing, and to act. The stars are waiting, not with promises of easy victories, but with challenges that define us. Will we remain in our cradle, content with what we know? Or will we step out, driven by that sea-like yearning, to claim our place among the cosmos? T.A.R.S. is a whisper of possibility, a spark in the dark. It is up to us to fan it into a flame. The universe is vast, its secrets hidden in the light of distant suns. T.A.R.S. offers a way to chase that light, to send our creations where we cannot yet go. It is a humble step, but a vital one. For in the act of reaching, we redefine ourselves. We become not just inhabitants of Earth, but citizens of the galaxy. The stars call to us, as they always have, and with T.A.R.S., we begin to answer.